Welcome to the video lecture for section 1.3. We'll be talking about functions, we'll talk about their definitions, some notation, and how to use them to evaluate values. So the general idea of a function is, by definition, a function is a relationship between inputs and outputs. The definition for a function is on page 24, definition 1.7. We define our inputs to be the independent variable, and our outputs are the dependent variable. Usually the inputs are x's and the outputs are y's, although those variables are not universal. So what a function does is it takes an input and it turns it into exactly one specific output. So if you take an input, your function is going to do whatever it does and turn it into an output. Alright. Now, it's never going to get confused if it really is a function. It's always going to know to turn this input into this output. So we can't have anything going to two different outputs. We can have two inputs that happen to turn into the same output. And we'll see many functions that do that type of thing. But generally speaking, the only thing we need to worry about is that every input gives us exactly one output when our function acts on it. This set of things that go into your function is also called the domain. And this set of things that your function produces from those inputs is called the range. And both of these sets are very important. In fact, a lot of times we'll see functions defined symbolically or verbally, and we don't mention the domain, but the function's definition, whatever function we're talking about, the domain and the range are always coming along for the ride. We always care about what we're allowed to plug in and what our function generates. If you refer to the notes on page 25, there are several different examples of different ways that we express functions, the primary ways being verbally, using a sentence to explain how the function works, or perhaps using a table of values that shows what the function does with certain inputs. It tells you the outputs associated with them. On the other hand, the representation of functions that we will see the most frequently in this course is the symbolic expression. So that would be a formula of the form maybe y equals 6x plus 3. Okay, what this function does with an input is it multiplies it by 6 and adds 3 to the result to generate the output. Now these formulas are the bread and butter of this course because we will get into how exactly the functions work and their domains and ranges. You can also represent a function using its graph, and we will often graph symbolic functions, and we'll have both of these versions to work with in terms of gathering data about a function. Now the sets associated with a function, a function's domain and range, can be discerned in any of these situations. If we define our function verbally, we might need to think about what inputs are allowed and what outputs could be generated. For instance, in the case of time being our independent variable and some physical quantity like height or number of gallons or temperature being the dependent variable, we generally don't let time be negative. So our domain would begin at 0 and go upward from there. Now we can also analyze the graphs of functions to determine their domains. And we'll look at a very strange looking graph. For the time being. And our other piece. Okay. So here we have a graph, and we would like to figure out what is the domain and range of this function. Well, the domain is the set of all possible inputs. In other words, all x values for which the function knows what to do. Now, our function has a gap here between -1 and 0, where it doesn't really do anything. Our function exists everywhere to the right of the y-axis, and everywhere up to and including -1 along the x-axis. So the shadow of our function, if we were to shine a light straight down or straight up, the shadow cast on the x-axis tells us the domain of this function. And we can use interval notation to represent it. Our function exists over to the left from -∞ up to -1. And since I am using a closed circle there, I'll include -1. Now there's a gap where my function doesn't exist, so I'm not allowed to plug in any of these x values in between -1 and 0. So I'll skip those. And since I have an open circle here, that indicates to me that my function also doesn't really know what to do if I plug in 0. So 0 is not allowed to be in my domain either. Alright. Now, in terms of range, we are going to look in the other direction. So sometimes it's nice to turn your page 90 degrees to one side or the other, and do the same type of thing. See where your function exists along the y-axis. Now, if I observe this function, it seems to go up forever, and it seems to go down forever, and it seems to hit all of these these y values in between. So it would appear that the range of this function is all real numbers from -∞ to infinity. This function spits out, it generates every single y value because it is level with every single point on the y-axis at some point in its life, at some point on the graph. So that is how you would handle examining the domain and range of a graph. Now, for now, we will just talk about the domain of symbolically represented functions. So here we see a function represented symbolically using a formula, and we would like to find its domain. Now, right now, we can assume that all real numbers are acceptable inputs. The only issue with this function is that x is under a radical, and an even radical. So we run the risk of taking the square root of a negative number. So that is where our domain comes in handy. I can restrict it so that I avoid doing that. And the way that I will avoid doing that is to say, well, x minus 3 can't ever be negative. Now, what does that imply about x? Domain is the x values that we are allowed to plug in. So if I add 3 to both sides of this, I see that x is required to be greater than 3. So that's one way I could express my domain. Alternately, I could convert that to interval notation and say 3 and up is acceptable. In a similar vein to the previous problem in the previous video, we might want to find the domain of a different function, a different type of function, which has issues as well. And this one is written in function notation. We'll say f of x equals 1 over 2x plus 1. Now, the difficulty that this function might encounter is if we were to plug something into the denominator which would make the denominator 0. So recall that the denominator expression, 2x plus 1, cannot be equal to 0. And now we can solve for x as if we were working with an equation, even though what we have here is an inequality. So if I if I subtract 1 from both sides, that leaves me with 2x cannot be equal to negative 1. And finally, I can solve for x by dividing both sides by 2, and I see that x must not be negative 1/2. And that would seem to be the only problem. So all real numbers will work except for this one. So this implies that our domain is the set of real numbers, negative infinity, up to negative 1/2, not including that x value, but also all real numbers greater than negative 1/2. And that is how we would describe that exclusion of negative 1/2. Now this is the first function that we've seen involving function notation, this f of x format. Now function notation is discussed on page 27 of the notes. The formal definition, definition 1.9, is a little bit clunky and doesn't really get to the heart of why we like this notation. The reason we like it is because it states explicitly which variable is our dependent variable, whatever is inside getting plugged in, and what is our dependent variable. Sorry, this should be our independent variable. I think I might have misspoken. And this function name represents our dependent variable. These are going to be our outputs, whatever the result of evaluating f at an x value turns out to be. So to see how that would work, let me evaluate a function, and we'll use another rational looking function, f of x equals 3x minus 1 over 2x at x equals 5. In other words, what we are trying to find is f of 5. So that entails replacing every x in the definition of the function with a 5. So 3 times 5 minus 1 over 2 times 5. And using the order of operations, I'll simplify the numerator and denominator. That's 15 minus 1 over 10. So 14 tenths. And we can reduce that down a little. These are both even, so this is actually 7 fifths. Alright, now what does that mean for us? Well, it means that the point 5 7/5 is a solution of this function. In other words, this point, when x equals 5 and the output is 7/5, is on the graph of this function, and that'll come in handy a little bit later on when we get to graphing functions that are more complicated than the linear functions that we're working with at the moment. Just to see one more round of how that works, let's evaluate f of 9, let's do negative 9, using the same function. So f of negative 9 is going to involve exactly the same process if I plug negative 9 into my function, as we might say. 2 times negative 9. My numerator, 3 times negative 9, would be negative 27. My denominator, negative 18. So, negative 27 minus 1 would give me negative 28 over negative 18. And we see that there are some common factors here. Again, both the numerator and denominator are even, so we can at least cancel a 2 out of everything. So, let's see, 28 would leave me with 14, and 18 would leave me with 9. Now, they were both negative, so a negative will also cancel, and that is our final answer. So, f of negative 9 equals 14/9. Another way to say that would be that the ordered pair, negative 9, 14/9, is part of our function. So it is worth mentioning that the domain and range and some other features of functions are also discernible when we have a function in in the form of a table, as we do here. So we can begin by asking if this is indeed a function. We always want to check that. Now, what I want to watch out for is any repetition of x values in the x row of this table. Because what that would mean is that one x value maps to two different y values, and that would mean this is not a function. So I would say that this is a function because every x value returns a unique y value. 1 goes to negative 2, 3 goes to 5, 5 goes to negative 1, 8 goes to 8, and 20 goes to 36. There is no ambiguity about what an input would produce as an output. So then the question is, what is the domain and the range of this function? Now, in the case of a table like this, the most that we can say in terms of what we're allowed to plug in, what inputs are available to this function, is the inputs that are provided. So I would say that the domain is the set 1, 3, 5, 8, and 20. Now these are the only 5 inputs that I know anything about, and as far as I know, this function can only digest those 5 numbers. Similarly, if those are the only 5 numbers that this function can take in, then the only 5 numbers that I know it can produce as outputs are the numbers in the second row, negative 2, 5, negative 1, 8, and 36. So that would be our domain and range taken care of. Now, we can discern information about what a given input does. For instance, here we're asking, what is f of 5? So we are asking, what does our function produce when we input 5? So I'll look for 5 in the input row and see what the output would be. So negative 1 is our solution. Now, the fifth part of this multi-part question asks us to look for the case where f of x is equal to 5 and to return what inputs caused that. So if f of x is 5, then what is x? Well, that happens when x is 3. So x equals 3 seems to be the only time when f of x is equal to 5.